So we are glad to have you here for Bogazici University Computer Engineering Department Mutlu Architecture lecture series here. And we are glad to have Professor Onur Mutlu from Carnegie Mellon University. We are going to have 3 lectures today, tomorrow, and Monday. That's going to be the first lecture, and then there will be another one next Thursday, Friday, and the Monday after that. So there are 2 separate lectures, and each lecture is planned to be 3 hours. And he's going to actually decide when he wants to give breaks. So without further ado, I'd like to welcome here again, and thank you again for coming.
Okay, thank you, Alper. Thanks a lot for coming. It's great to be back in Bogazici. I have actually a lot more material than 3 lectures, I think, or 9 hours. I was up until very late last night, like 4:30 a.m., partially because of jet lag. But I'd be happy to go longer if people are interested in going longer. And I don't think we're going to cover all of the slides here. So I actually structured this like a mini course, but I think it's 9 hours is too short for a mini course. So we'll try to do as best as we can. I normally have reading assignments too, so if you do the readings, that'll be the best way to get the best out of these lectures. Okay, this is my agenda for today. I'm happy to change it. I'll talk about some logistics, info requirements, who am I, and what you will learn, and how you can get the best out of these lectures. And I'll give an outline of the lectures this week and the next. And I'll also provide some readings for next time. And hopefully we'll do a deep dive into the course material. Let me adjust this so that this works. This is my first experiment in the recording also, so we'll see. At least recording on my own. So there are 2 mini courses. One is on multi-core architectures and shared resource management. And I'll talk about both fundamentals and recent research. Normally, this is a much longer course, I think, maybe 20 hours or so. So we'll try to fit it into 9 hours. So you can imagine how packed it'll be. And the second will be on memory systems. These are both very important topics, in my opinion. What are these about? These are very hot portions of computer architecture research and practice today. Many companies are interested in this, and many researchers are interested in this for a good reason, and hopefully I'll convince you of the reasons. There's a very large design space in both areas, and there are many opportunities for innovation and groundbreaking research. And we'll focus on major aspects of multi-core design, fundamentals, trade-offs, and cutting-edge research. And I'll hopefully focus a lot on trade-offs, advantages and disadvantages of different approaches. There are 2 goals that I usually set. These are actually goals for many of my classes too that I teach at Carnegie Mellon. First is to build a strong understanding of the fundamentals of multi-core architectures and the trade-offs made in their design. Examine how cores and some of the shared resources can be designed. And the focus will be, well, the trade-offs again. And the second is hopefully build an understanding of the state-of-the-art research in this area and research problems in this area also. I'll mainly talk about some of the papers that we've been looking at, some of the ideas that we've been looking at. And for those of you who are studying in the area, the best way to get out of these lectures is to actually read, critique, and discuss these research papers themselves. And I'll give you a lot of pointers as we go along. Some of the old papers too. Like I'll probably spend some time on Amdahl's fundamental paper from 1967. Okay, who am I? I don't think I'll cover this a lot, but I teach at Carnegie Mellon University. I got my PhD from UT Austin, worked at Microsoft Research, Intel, and AMD. And you can find information about me online. And I'm interested in many different things: computer architecture, hardware, software interaction, which being in the middle of everything, but many core systems, memory systems, a lot of interesting things like hardware fault tolerance and security. We're doing a lot of research on memory fault tolerance, and that will be part of the subject of the next class, lecture 2. I'm actually very interested in bioinformatics also, so if people are interested in that, I'd be happy to talk about that too. But I think if I had to summarize it, I'm interested in developing efficient, high-performance, and scalable systems in general. Today, it happens to be multi-core and memory systems, and solving different architectural and design problems at low cost and complexity. Because in the end, those approaches that have low cost and complexity have the most potential for impact going into the future. A little bit more about my group. These are some slides just so you get familiar with the people who have done the research that I'll actually describe. This is the picture of our department that I took, I guess, one kind of dark night. I'm from that department. Pittsburgh happens to be a good place to live in the United States. And you probably know about Carnegie Mellon. It's actually a very small school. I don't know how it compares to Bogazici, but it's a relatively small school. But we do a lot of research. There are a lot of Nobel Prize laureates, as well as Oscar winners, because Carnegie Mellon happens to have a very strong drama department in theater. And yeah, it's a small school. I don't know how many students are there in Bogazici. 10,000? Maybe it's comparable.
Roughly the same.
Roughly the same? Oh, okay. So Bogazici is considered a small school in my opinion too. I went to some big schools. UT Austin was where Alper also went. I think 56,000 students at the time. Okay. And this is my group so far. You can find a lot of the publications and information in there. And these are some of my students. These are all pictures. We had a lot of fun doing research also. Okay, who should attend this course? Hopefully you're here because you're interested in computer architecture. I'm interested in it. I'll assume some computer architecture basics. This won't be a very basic course. I will not be talking about pipelines or caches, the basics of that. But if you have questions, please ask. And I think the most important thing is the attitude in general. Be ready to ask questions, think hard, read papers, and focus on trade-offs, and discover on your own. Probably this may be the most important thing in the end. I can give only so much, right? The rest is what you can do with it. So this is what I'll assume, familiarity with basic computer architecture. How can you make the best out of these lectures? I think I've already told all of this, basically. If you have questions, please ask. We don't have to cover all of the slides. I'll try to cover some of the basics, but the best will come out if there's good discussion so that we can go in depth. And the second thing is if you can read the discussed papers and explore on your own, then you can do bigger research on some of these areas. Homework, I like giving homework if you ask my students. So the first homework is simple, actually. It's due tonight at midnight. Midnight is early for me, but please send me an email so that I can know who is taking the class with your name, your picture, interesting fact about something personal to you. You can pick anything you would like. Why are you interested in these lectures? And what do you expect to learn at the end of, I think, 18 hours total? And anything else you would like to share or ask. So hopefully this shouldn't be too hard of a homework for any of you who have sent email before. Okay, and my email address is very simple. It's my first name, onur@cmu.edu. And you can find it online. Okay, so this is the aggressive schedule that I built, which we're not going to be able to finish. But lecture 1, I'll talk about why multi-core, some of the basics of parallel processing, some alternatives to multi-core, and some trade-offs. I'll talk about symmetric versus asymmetric multi-core systems. This is building upon some of the things that I covered last time I visited. And lecture 2 will be shared cache design for multi-cores, which is an important shared resource. Cores actually share caches. And today, actually, most of the effort in designing a system is really spent on designing the memory system and the shared resources. And shared cache is a very important one because if you hit in the cache, you don't need to go out to the memory system. And a lot of the algorithms today are focusing on how can we keep the data on chip so that the processor doesn't need to go off chip and spend a lot of energy, consume a lot of power, and wait for long to access data. That's why I put this as a second part, shared cache design. And if time permits, we'll do interconnect design for multi-cores. And this will also be determined partly based on your interest. So if you email me tonight and you all tell me that I don't want caches, I want GPUs and data parallelism, I'd be happy to talk about GPUs and data parallelism also. So lecture 3, if we ever get to it, will be data parallelism and GPUs. That's why I said if time permits. My feeling is we'll cover only lecture 1 and lecture 2, given the pace. But I'm happy to try to get to lecture 3 also. So if all of you tell me that this is better, or if you have feedback right now that we should go into something, we should try to get to lecture 3 material, I'd be happy to.
Maybe lectures can be longer, not only 3 hours.
Okay, as long as people are okay with it, I'm fine with it. I can actually go for much longer than like 8 hours or so, but I find that the attention span drops quite fast. But I'm happy to do that too. So this is a very exciting topic also, data parallelism and GPUs, and but we'll try. Yes.
I am an instructor, so I am just only interested in lecture 2 if time permits and lecture 3 if time permits.
Oh, this part you mean interconnect design?
Yes,
and
prefetcher
prefetcher design. Okay. Okay. So if you guys send me feedback on these, that'd be great tonight. And we can share the slides, hopefully, so that everyone can send feedback. And I can talk about everything, actually. That's not a problem at all. Okay. Yeah, but do not believe all of this tentative schedule. This is all statically scheduled, and we're seeing one example of dynamic schedule right now, right? Systems that perform best are usually dynamically scheduled, right? And this will be the first topic of this course, actually. Static versus dynamic scheduling. So this is the static schedule I came up with yesterday. Well, actually, it was much before yesterday, but this already changed almost based on the feedback that we received at runtime, right? We have a dynamic feedback right now, and we'll cover some of this. And a lot of the things in parallel processing are actually require dynamic scheduling. And I think that's why this is such an important topic that I would like to cover it briefly. And it fits the topic here also. So what is static versus dynamic scheduling? Static is done at compile time or parallel task creation time. Whenever you create something, you statically say this goes here, this goes here, this goes here, this goes here. That's what I did. I created a lecture schedule, right? I said this topic goes to lecture 1, this topic goes to lecture 2, this topic goes to lecture 3. And the schedule does not change based on runtime information. On the other hand, dynamic means done at runtime. This is after tasks are created, after you figure out the schedule. And this schedule changes based on runtime information. And this happens in many, many different places, not only in computers, but also in life in general. So one example is parallel task assignment, which is fitting the topics we're going to cover. The problem is simple. Actually, a lot of people have studied this problem theoretically also. You have n tasks, p processors, and n is greater than p. Do we assign tasks to processors statically in a fixed way or dynamically in an adaptive way? Static assignment, basically one option of static assignment is say task 0 goes to processor 0, task 1 goes to processor 1, ... and you round robin. This is simple, right? There's no movement of tasks, and it's very easy to do the assignment. That's always the advantage of static scheduling. It's usually simpler. But it's usually inefficient because it underutilizes resources when the load is not balanced, right? So what does this mean? You probably know about load balancing. Basically, if one task is much greater than some other task, now you're underutilizing the resources, underutilizing the processor where you assign the smaller task to. Right? Because that processor will be done quickly, and it'll be twiddling its thumbs. It's going to be waiting for a long time. Whereas dynamic assignment, that's exactly the reason dynamic assignment is much better. It's efficient because it better utilizes processors when the load is not balanced. And I'll give you an example of that. But the downside is usually this more complex. And we'll see that complexity tonight when you send me the lecture choices. And I'll have to do a complex decision because there will be conflicting choices probably. And in this case, the complexity arises from moving the tasks to balance the processor load. Somebody needs to do this, right? Who does it? Software, hardware, and people have proposed different solutions to it. But there needs to be complexity somewhere in the system to do this. And you get higher overhead also. When you do this, no movement of tasks, there's no overhead, right? You've done scheduling already statically. Whereas here, task movement will take time. And it can disrupt locality also. If you keep the tasks that happen to share data at one location, now if you're moving that task somewhere else, you need to move the data also. And we will actually see this problem when we talk about bottleneck identification and scheduling. And moving critical sections to a large core. We will see that locality of some data will be disrupted. Okay. So one example of this is, I like this example because you compute a histogram of a large set of values. For example, let's say you have a book and you're trying to find how many times a word appears. You're trying to figure out the 29 letters, I think, how many times each letter appears. What you can do is you can divide the book into portions, like pages, maybe every n pages, divide the values across t tasks, and each task processes n pages, and each task computes a local histogram for its set. Each task produces a histogram for the 29 letters. And eventually, the local histograms may be merged with global histograms in the end. And this is not the best algorithm. This is actually a pretty bad algorithm for this. But the idea is basically these are parallel tasks. They are partitioned. The book is partitioned across the tasks. And the serial part adds those local histograms to a global histogram, which necessarily is a critical section because the global histogram is a shared data structure. And that's exactly the reason why this is not a good parallel program, because you've created this huge critical section that aggregates everything. You could do this much more nicely in a pipeline parallel way, but we're not going to talk about that. But this is just to give you an example. This parallel part actually can be very imbalanced, right? It could be that some pages, let's say you've divided the task into 10 pages, you get 10 pages with pictures. There are no letters, right? That task finishes very quickly. Some other task gets 10 pages with all text in it. And it may be that some task gets 10 pages with all A's in it. I don't know if somebody writes a book that way, right? You probably watched the movie The Shining, where every single sentence is, I guess, all work and no play makes Jack a dull boy. If you get a book like that, then the histogram is relatively easy to generate. You get very good locality. But if you get a book like 100 Years of Solitude from Gabriel Garcia Marquez, that'll be much more sophisticated, probably. And you will not get that much locality. So those tasks will have different lengths in terms of execution time, because their locality would be different, because the data values they're processing would be different, and you would get load imbalance because of the input data to the tasks. And that's why static scheduling doesn't work too well, because these tasks will be very different. So how do you schedule the task updating these local histograms? In the previous case, static, you can assign equal number of tasks, equal number of pages, and that has a downside as I described. Dynamic, you can assign tasks to a processor that is available. You still chop the tasks into n pages, let's say, but you don't say these n pages go to this processor, these n pages go to this processor. You create some queues like this, and processors pull, whenever they're idle, they pull the next n tasks from this queue. Then the question is, how do you actually implement these queues, right? Do you have a single shared queue across the processors, such that whenever a processor becomes idle, it pulls the next n pages? Or do you have distributed tasks like this, distributed queues like this? Each processor has its own queue, and initially someone assigns the task to these queues. And whenever a processor's queue becomes empty or close to empty, the processor now steals tasks from some other queue. This is called task stealing. And you can have another task stealing implementation like this. You can have smaller queues over here that are still private to processors. And when the processor, and you have another shared queue that fills in these smaller queues. And there are advantages and disadvantages to all of these approaches. We could actually spend a lecture talking about advantages and disadvantages. But given the time we have, the biggest disadvantage to the shared one is it's a centralized resource, right? And whenever a processor needs to access this shared queue, you need to lock it. So now you have a critical section accessing this shared queue, and you have a bottleneck. And the biggest advantage to this is the processors can privately access their own queues without notifying anyone else. Only time the processor needs to notify someone else, which means lock, synchronize with another processor, is when it's stealing a task from another. And hopefully it won't be stealing too often. And if you do something like this, then the processors know exactly where to steal tasks from. It's the shared task queue, right? Here, it may be difficult to determine where do you steal the task from, right? There's one problem. Well, there are actually two problems here. I'll just briefly mention this. If you have any questions, please feel free to ask. But one problem is, which other processor do you steal the task from? You would like to figure out perhaps the processor that has the highest load. But how do you know? You may not know, right? Unless you keep some metadata. Now we're getting into the overhead. That metadata requires some overhead. So you need to know, or you need to perhaps keep track of the other processor's load. And to be able to keep track of that load, now you have a shared data structure, right? And that's another critical section for you. Here, you don't need to keep track of the private queues of the other processors. You just need to keep track of what's in the shared queue. And that's hopefully known by design, right? Now it turns out that these two approaches perform similarly in practice. And in practice, many people employ random task stealing, randomized task stealing. They randomly steal from some other processor. Even if you don't do it intelligently, it happens to work well in practice. But that's not always true. You will get applications, with parallel applications with dynamic task creation where this won't work too well. Any other advantages or disadvantages that you can think of? We can actually go through all of this. I didn't do a very formal treatment because this is not the main subject of the course. But you can see that with every single design, you have a good disadvantage and a good advantage or a bad disadvantage.
Of course, it all depends on the task granularity, right? If we're not going so frequently to the shared resource, this is probably the criteria to decide.
Absolutely, yes. It does depend on task granularity too. If your tasks are very large, you may not be going to the shared resource that much. That's right. And that's another trade-off, because if your task is very large, now you may get more load imbalance also, potentially. Because now you're more susceptible to the input values that are in your task. But that's a great point. So later on, we'll talk about finer grained parallelization. If your tasks are very small, and if your overhead is very small, you can hopefully do the load balancing much better. Okay, so task stealing, I already told you about. When a processor task queue is empty, it steals a task from another processor's task queue. There are two questions: whom to steal from and how many tasks to steal. This enables dynamic balancing of computation load, but it requires additional communication and synchronization overhead between processors. And I think this is the second problem that I forgot to discuss earlier. There were two problems with this design. One is whom to steal from, and the second is when do you stop, right? You need to know to stop stealing if there are no tasks to steal, right? This is kind of like the halting problem. Not exactly, but similar. Okay. Who does the assignment is another question here, hardware versus software. And whenever we talk in this course, hopefully this will, you'll think of different trade-offs between software and hardware. A lot of the things that I'll describe can be implemented in software also with additional overhead. And usually, software has better scope because software can analyze a lot of things, right? At least offline. Online, if it analyzes many things, it has more time overhead. It still has better scope. But the downside, it has more time overhead, because in software, you'll need to process instructions and you'll need to figure out which task to steal from. It's also slow to adapt to dynamic events. For example, a processor becomes idle, it doesn't get communicated to the software very quickly, especially in today's systems. On the other hand, hardware has low time overhead. It can quickly adapt. It can adjust to dynamic events faster. The downside is, well, I guess the downside is also it doesn't have a lot of scope. Although scope comes with additional complexity, that's the downside. And it does require hardware changes, which leads to area and possibly energy overheads. But keep in mind whenever we talk about things later in this course, this software-hardware trade-off, where do you draw the line? Like who does what? Ideally, we would like to take advantage of the software's capabilities as well as hardware capabilities, best of both worlds. Okay, how can the hardware help in this case? I'll not talk about this in detail, but I'll point you to a paper that talks about hardware task queues. The problem is managing task queues that I showed you in software has overhead. This overhead is especially high when task sizes are small. If you have big task sizes, you can amortize the overhead of scheduling those tasks. But people have been looking at hardware task queues. Part of the queue is implemented in hardware, and each processor has a dedicated task queue, and software fills the task queues once in a while. And you can imagine different policies for filling the task queues, right? Not when the task queue is empty, but before the task queue becomes empty. You can do that. And the hardware manages the movement of tasks from queue to queue, because this synchronization in hardware is much faster. You can actually have barriers implemented in hardware such that you can synchronize between the different queues. And now there can be a global task queue as well. You can have hierarchical tasking in hardware. And this paper discusses the trade-offs between hardware task queues as well as software task queues and cooperative task queues. And if you're interested, this is a paper from Intel, from ISCA 2007. There have been other works that built upon it. And if you're interested, I'd be happy to point you to those. So this is just one example. So when you actually dynamically create tasks, you can still do static assignment based on the task ID. Here is one example. I think basically you have a problem, you divide the problem into subproblems, and these subproblems are created dynamically. I think my favorite example, I don't think I have anything to, oh, do I?
In the drawer.
In the drawer. Oh, okay. Well, my favorite example is a mouse looking for the end of, you have a maze here, and you have a mouse that's starting in the beginning, and basically you have some obstacles in the maze. And the idea is you create an algorithm that gets the mouse from the entrance of the maze to the exit of the maze. And you can actually design this as a parallel program that does breadth first search, right? You can create tasks that search to the right, down, to the left, and to the top. And every time, basically, you explore, each task explores that direction. And each task creates another task that explores the adjacent direction. This way, you're basically creating new subproblems. You're partitioning this maze into smaller tasks, and very, very fine-grained tasks, if you look at it. You could actually partition in a coarse grain also. That's another way of looking at the problem. But if you do it in a very fine grain, now you have a lot of tasks that are created dynamically, and you need to somehow assign them to different locations. And static assignment usually doesn't work in these dynamic task creation cases. Okay. Okay. So I think I'll go back to the topic of the course. But when do we really want dynamic scheduling? When we have uncertainty in dynamic events. If we do not know the result of an event, we would like to do dynamic scheduling. Right? If we do not know, for example, the balance, the input set of a task, we would like to do dynamic scheduling because we are uncertain how long the task will take. If we know exactly how long each task will take, then we can do the scheduling perfectly. Right? This another example here is out-of-order execution, which we will talk about in this lecture. You probably know that existing processors execute instructions out of order. Right? The compiler does scheduling of instructions. For example, it schedules instructions this way. You have a load, add, multiply, divide, another add, and a branch. And some of these may be dependent on each other. Right? This is the static schedule that the compiler provides. But today's processors do out-of-order execution, which is dynamic instruction scheduling. If an instruction cannot be executed because it has a data dependency, for example, this load missed in the cache, the processor can look ahead and find an instruction that is independent of the load that can be executed. Maybe you have another add here that's independent of this load that has nothing to do with the data value of this load, and the processor figures that out and executes it. That's the idea. So if this is really needed if you do not know the latency of the instructions. If you not know actually three things. One is if you not know whether the load is a hit or miss. Right? If the load is, if the compiler doesn't know if the load is a hit or miss in the cache, then the compiler cannot figure out where to schedule the dependent add. Let's say this add actually reads the value that the load loads into register 1. If this load takes 1 cycle, if it hits, versus 500 cycles if it misses, then the compiler cannot know where to schedule the add, right? If it takes 1 cycle, then add should come right after the load. If it takes 500 cycles, then add should come maybe 500 instructions after the load. But the compiler doesn't know this information, and compiler is uncertain. That's why hardware dynamically scheduling the instructions can do a much better job. Of course, dynamic scheduling comes at the expense of additional hardware, which we will talk about, which led to the multi-core in the end. And the expense of additional hardware is hardware needs to have logic to figure out, is this multiply, is this divide, is this add, is this branch, is this add? Are they independent of this load, right? And the question is, how do you do that? You have a search that happens that searches whether, that checks whether the sources of any of these instructions is the source, the destination of the load. And the problem is even more complicated because you have now dependency chains, right? Okay. Yes, sure.
This check can be static, right?
This check, oh.
Dependency check, does it have to be dynamic as well, or I think it can be static?
Which depends, check, whether the add depends on...
The add depends on this load or whether the multiplication depends.
So that check can be static, that's right. But whether or not the value is available needs to be dynamic.
Okay.
Because you do not know whether this value is available. You can determine the dependency statically. And you can communicate that information to...
Where to schedule that one, either in one cycle or in 500 cycles.
That's right, yes. Yes. And the compiler cannot do that well. Now there can be other checks that cannot be static. For example, if you do not know the memory address of an instruction, which are usually determined dynamically. And that's another reason why you cannot actually do static scheduling really well in the compiler, because you do not know the memory address of a load or store. And you have a store instruction here, and you have a load instruction here. And you do not, store is storing into X, load is loading from Y. And the compiler may not know whether X and Y overlap, right? And the compiler may not be able to figure out whether it can reorder this load and store. Okay? And that again is another uncertainty. The compiler doesn't know. It doesn't have knowledge of the dynamic information. And the third example is actually the branch direction, right? The compiler doesn't know the branch direction. So it's hard to schedule the static instructions. Okay. So let's get back to the schedule of the course. With that in mind, this schedule is very static right now, and it will probably change. And this is the first set of lectures that I've discussed. The second set of lectures, I have another set of lectures coming June 13th, 14th, and 17th. And this will be on memory systems. And I'd be happy to get your feedback on this too. Again, the static schedule is I'll talk about main memory basics and DRAM scaling in lecture 1. I'll talk about emerging memory technologies that are interesting to examine today, that are likely to replace some of the technologies that we are seeing. For example, today's main memory has been built using dynamic random access memory cells, but there are many emerging memory technologies like phase change memory, spin transfer torque, magnetic memory, and potentially resistive RRAM that could potentially replace DRAM. And I'll talk about those and hybrid memories. And finally, lecture 3 will be on main memory interference and quality of service. And I didn't put if time permits over here yet because we didn't go fine grain yet. These tasks are coarser grain at this point. Okay, some readings. I hope we'll be able to distribute some of these, but we have your email addresses. Okay, so these are some of the papers I will talk about. Again, we may not be able to cover, but these are the papers that I'll describe. Not all of them probably, but you will get these. And there are some recommended readings also. And there are videos of some of these papers too, so if it's easier for you to get information in that mode, we have some videos, although these don't cover all of the papers. This is readings for lecture June 7. Again, this is a very static schedule. I'll talk about caches, and there are some recommended readings also, and there are some videos also. We'll distribute this slide so that you can have access to all of these. And these are the leading readings for June 10th, assuming that we're going to do some interconnects over here, but we'll see. And if we can do GPUs and SIMD processing, then there are some videos about them as well. Okay, so if you want to get more information, a lot of the material, basic material, is covered in the online lectures, and I have all my lecture slides online. So if you'd like to ask any questions about them, you can access everything from CMU's website. And recent research papers are over here too that I'll talk about. Okay.
Before you
yes.
proceed, some of our students here working on that dynamic task scheduling thing, they're devising novel algorithms and things, but when it comes to testing their ideas to see if it's beneficial or not, they're having difficulty to find good examples that this will really be beneficial. Mm-hmm. Can you say certain generic problem domains fit to that so nicely, or is there a tool that tells you that this application fits to dynamic scheduling well, kind of thing? Do you have any guidelines on that? So
that's a tough problem. But that I empathize with them because that's a tough problem. Like how to figure out. I think there are two questions. One is what kind of applications do you want to test the algorithms with?
Regular scientific application, and which does not fit to that because it should have a dynamic nature. So
That's right.
this will be beneficial. But are there some generic domains that you can say, you can take your examples from that domain?
That's right. So I don't think there are generic domains themselves, but scientific applications, I agree. The traditional scientific applications, they're more bulk synchronous. They're based on the bulk synchronous processing paradigm that is not dynamically scheduled. You can turn them into dynamically scheduled, but they're very irregular. So static scheduling probably is a reasonable idea for some of them. But I can point them to some references, like this paper. Points to some references. It'd be good to look at that paper.
Profiling tool that may tell you that dynamic scheduling fits to that nicely? Or?
I don't think there is a magic tool like that. I wish there was. Maybe that's a good research topic. But there is another book, Parallel Programming Patterns by Tim Mattson, that could give some hints. But again, that doesn't exactly answer the question that you're asking, I think. I think the question you're asking is a tough one. And it'd be great to see a study related to that. What kind of problems fit the dynamic tasking versus static tasking kind of parallel programming better. I'd be happy to brainstorm about some of that, but it's very hard to give an answer, I think, saying that this kind of problem fits better versus this kind of problem fits better. Because like I think this kind of problem may be better with, this is one example, but it's hard to generalize this. Whenever you create tasks dynamically this way, your search is dynamic. I think that's one example. Okay. So I think we can take a break after 1.5 hours. Is that reasonable? Okay, everybody will be. We can take. Yeah.
At the 1 hour.
Oh, do you prefer it 1 hour? Okay, 1 hour then, because we have. I guess in this case, technology determines the schedule. There you go. Another dynamic event, right? It's not. Lots of different dynamic events. Okay, some basics. What's a parallel computer? Because we're going to be talking about parallel computer architecture. Definition of a parallel computer is actually not really precise. A parallel computer, this is George Almasi and Alan Gottlieb in their old book, Highly Parallel Computing, define a parallel computer as a collection of processing elements that communicate and cooperate to solve large problems fast. Now this is very vague, right? What is a processing element? What is communication and cooperation? And what is a large problem? And what is fast, right? There are many things that you can take issue with here. And according to this, is a superscalar processor a parallel computer? Is a single-thread processor a parallel computer? Well, it has a collection of processing elements. It has multiple execution units. They communicate. They have bypass buses. They cooperate to solve a single problem. And then hopefully it's a large problem. And they try to be fast, right? Then it is a parallel computer too. And I would argue that everything is a parallel computer that fits this definition. But for this lecture, for multi-core architectures, we'll talk about a processor that gives the illusion of executing a sequential ISO in a single thread at a time is a sequential machine. Almost anything else is a parallel machine. Basically, if you don't have a single thread of execution, and if that illusion, von Neumann model, is not perfectly maintained, then that is a parallel machine. Okay. Examples, if you have multiple program counters, definitely that's a parallel machine because von Neumann model doesn't consider multiple program counters, right? You have a single program counter. Data flow is definitely a parallel machine because there's not even a program counter in a data flow model of execution, right? Every instruction wakes up its destination instructions and an instruction, a node, fires when its operands are ready. Multiple data being operated on simultaneously, GPUs or SIMD architectures, vector processors. And some combination of any of those are parallel machines. I think this builds on Flynn's taxonomy of computers. This is a seminal paper by Mike Flynn that divided computers based on 2 dimensions, based on how many elements each instruction operates on and how many instructions that can be executed from different streams at the same time. You can have single instruction, single data machines. We have a single instruction operating on single data element. This is a sequential von Neumann machine. You can have single instruction, multiple data machines. Basically, a single instruction operates on multiple data elements at the same time. Array processors or vector processors are this kind of machines. GPUs are today are vector processors and array processors also, a combination of those, and hopefully we'll get to them. I'll skip MISD, but you can have MIMD, multiple instructions operating on multiple data elements. These are basically multiprocessors and multi-thread processors, and our focus will be on these today. MISD is a tough one. Basically, you have multiple instructions operating on a single data element. That's a little bit hard to think of also. The closest form I can think of is a systolic array processor. Basically, you have an data going in to multiple sets of instructions, and data gets transformed to some other piece of data to be operated on another instruction over its time. It's not exactly like that, I think. You're not really operating on a single piece of data element. You can argue that that data element gets transformed, and that's a different data element now, right? Parallelism, so why do we have parallel computers? Parallelism is doing multiple things at the same time. Things could be many things: instructions, operations, and tasks. And the main goal is to improve performance, basically execution time or task throughput. And we'll talk about Amdahl's law briefly. But there are actually other goals as well, and it's good to keep these in mind when we talk about these. Can anyone think of what the other goals are, other than improving performance? No?
Reduce energy.
Reduce energy, right? Reduce power consumption or energy consumption. Basically, you can design more units at lower frequency that can consume less power than a single unit or fewer units at higher frequency. And this is actually one of the motivations for multi-core also, because you have a very complex single-threaded processor. You design it to operate at high frequency to get high performance. And the trade-off is that you can actually break it up into smaller units that operate at much lower frequency. Do you actually design a single-threaded processor that operates at 1,000 times frequency than 1,000 processors that operate at 1 unit of frequency? Well, in terms of energy consumption, you'd probably want to design this one, right? Because the dynamic power consumption is correlated with frequency, not in a linear way, but in a cubic way. If you think about the power equation, probably you've studied this in your classes. It's capacitance, voltage square, frequency, right? And you have some activity factor here. And you can reduce the frequency to reduce power. And when you reduce the frequency, you don't need as much supply voltage also. You can reduce the supply voltage linearly as well. Now you have a cubic relationship here. So you can reduce the power in a cubic manner while keeping the performance the same. The hope is that the performance of this is the same because you can perfectly parallelize your program. Now there's that assumption over there. You can perfectly parallelize your program. So you can get much better power consumption if you keep the performance the same because you can reduce power consumption.
The factor that we have to consider is that when you parallelize the computation, the communication comes into picture, and the power consumption due to communication might increase the power consumption much more than you can think of.
That's right, exactly. Exactly. All of, when you add additional overhead to satisfy the parallelization, then you can get much worse power consumption. But this is one of the goals and this is one of the major reasons why industry went to multi-core, to reduce the power consumption, because it was much more power hungry to design a processor that has much higher frequency. Yeah. But that doesn't mean that we will keep the same performance, because there's another part of the equation. This is actually dynamic power. There's also static power consumption. And if you increase the execution time, now you're actually consuming much more static power in the entire system. So your power may go up. And you have additional overheads, as you said, which we will get into. There are other overheads as well. What other goals? There are some other goals too, actually, if you would like. Some other reasons to do parallel processing or multi-core. Multi-core is essentially a parallel computer on a chip. That's simpler, that's right, yes. Second is improve. I bulk it into improving cost efficiency and scalability, reducing complexity. Basically, it's harder to design a single unit that performs as well as n simpler units. Again, the assumption is that you can perfectly parallelize your program.
You can perfectly build up your communication channel.
Or that's right, yeah, you can also do that. But if you can perfectly parallelize, you don't need to communicate. That's the beauty of it. Yeah.
Then your data is also in parallel.
That's right, exactly, if you can do that. But again, this is one reason also. Another reason that's said because that has been given for the movement to multi-core, because it's simpler to design many simple cores and stamp them out. Is great. Is there another goal? This usually tends to be the toughest one to.
Of course, once you have that redundancy, you may always think about fault tolerance and reliability enhancement kind of thing.
Exactly, yes.
There's a dilemma there. You see, you have redundant resources. We used to think that whatever you put into the system, you have to utilize it to the maximum, improve performance. Now you say you may use some of those cores for reliability purposes, redundantly executing tasks and things, but power concern says do not use it.
That's right.
Shut this off.
That's right, yes.
Like this.
That's right, yeah. These are all trade-offs, right? You can trade off between performance and power and dependability. Maybe this is a harder trade-off once you design the system, unless it's reconfigurable. But you're right, you're absolutely right. So assuming that you don't have multi-core, this may be a reason to do just adding one more core, right? If your application is so important to keep dependable, you might want to do parallel processing because of this reason. Because you can have now modular redundancy, you can have multiple processors, and you can check. Basically, you provide redundant execution in space, right? You have multiple processors, and you check their outputs before retiring an instruction. Actually, before multi-core, for applications that were so important, people have designed parallel processors for this purpose, right? Like tandem computer, you probably know very well. They've designed multiple processors, and they check the output. And in the end, if the outputs didn't match, you had an LED that lit up, and a red LED, and the operator could go and figure out which computers in the data centers of its time had the LEDs lit up so that they could replace the faulty ones. So you could have this goal independently of performance if your application is so important. But this is an added benefit too. Okay, some types of parallelism. You can actually have parallelism at many levels also. Instruction level parallelism, here different instructions within a stream can be executed in parallel. And this has been the traditional way of exploiting, improving performance in a single thread. And we will talk about the scalability limits of this. Basically, people have been pipelining processors deeply, employing out-of-order execution with larger instruction windows, larger buffers through which the hardware can look at so that it can find independent instructions. That's called the instruction window. And as you increase the size of this, it becomes harder and harder to build the logic in an efficient way to figure out what instructions are dependent or independent of other instructions. And other techniques like branch prediction exploit instruction level parallelism, and very long instruction word machines, which we will not talk about. Data flow is a way of exploiting instruction level parallelism. The second kind of parallelism is data parallelism. Here, different pieces of data can be operated in parallel, in parallel. And vector processing and array processing. And this is very efficient in general. If you can do the same instruction on 1 million data elements, now you reduce the control complexity, right? You don't need to decode the same instruction over and over. Systolic arrays and streaming processors are examples of this too, and I'd be happy to talk about these. These are actually very exciting processors in my opinion. These are different execution models. And the third is task level parallelism. Now you have different tasks and threads that can be executed in parallel. Multi-threading and multiprocessing is very good examples of these. And we'll see the limits of instruction level parallelism that motivated the move to this task level parallelism on chip, at least. And data parallelism also affects things because it's simpler, but it's more specialized. Okay, so how do you actually create task level parallelism? That'll be our focus for a while. You can partition a single problem into multiple related tasks, related threads. You can do this explicitly. We have parallel programming. And this is usually easy when the tasks are naturally in the problem. For example, web and database queries are, arguably, it's easy because you have so many queries that are going into Google, and Google doesn't need to parallelize each of their queries. Now, that's not exactly true because of Amdahl's law. Even Google today realizes that each query may take very long, and it's bottlenecked by the slowest processing that happens in the entire stream in their data center. And even they're trying to improve the performance of a single query today. But if you look at a query level, this is easy. But this is difficult when natural task boundaries are unclear. And that's the difficulty in parallel programming. You can also do this transparently and implicitly. You can take a single-threaded program and transparently, speculatively parallelize it. This is called thread-level speculation. And I will not go into this, but this is another research area that computer architects have looked at for decades. The second way of creating tasks is easier, arguably. You can run many independent tasks or processes together. And people have been doing this for a long time, right, in multi-programmed machines. And this is easy when there are many processes. For example, if you have batch simulations, different users, if you have cloud computing workloads where you aggregate lots of workloads from different people, this is easy to do. But this doesn't improve the performance of a single task. This improves task throughput overall. OK, so a little bit of caveats before we take a break. You all know Amdahl's law. Basically, it says that your speed up is really limited by the non-parallelizable portion of the program. If you have a parallelizable fraction of a program P and number of processors N, the speed up that you get by employing that number of processors is 1 divided by 1 minus P, because you cannot parallelize this part, plus P divided by N. Here, if as N goes to infinity, your speed up approaches 1 divided by 1 minus P. And N goes to infinity means you keep adding more processors. Now, this is a beautiful law, assuming that your problem is serial versus parallel, right? Perfectly serial, perfectly parallel. And life is not that beautiful in general. And how many people have read this paper, Amdahl's paper? One. That's great. I'd encourage you to read this paper. This is a beautiful paper, actually. It's only 3 pages, as far as I remember. Or maybe it keeps going down. You can squeeze it down to 2 pages. But Amdahl was very pessimistic about parallel processing at the time. And he says in this work that it says basically validity of the single processor approach to achieving large-scale computing capability because of this serial fraction. He examined a bunch of applications, and he saw that serial fraction is not very high, let's say 60%. Parallel fraction is not very high, let's say 60%. And the maximum speed up you can get, even with an infinite number of processors with 60%, is a little over 2, right? It's not that much. Basically, that's what it says. You have a serial bottleneck, and your maximum speed is limited by serial portion. But there are several things that Amdahl's law doesn't consider, which I would like you to think about, and that will be the subject of the later part of the course. Parallel portion is not perfectly parallel. This doesn't hold also, right? P divided by N doesn't hold, because you cannot perfectly parallelize your program, as we discussed. There are 3 major reasons, and if you find a fourth fundamental reason, I'd be happy to buy you dinner or something. But first is synchronization overhead. The different tasks need to synchronize. They need to update shared data. The second is load imbalance, as we discussed. You have load imbalance, you have imperfect parallelization. One task finishes early, and the other processor becomes idle. Basically, you're not using your N very efficiently in that case, so you cannot divide it by N anymore. And the third is resource sharing overhead. Whenever these processors share resources, they contend with each other, and you get additional overheads. Some of them get delayed. And as a result, this P divided by N doesn't work out very well because you have this additional delay that happens. And we will talk about actually pretty much all of these. Resource sharing overhead we'll talk about in the memory systems part of the course also. And synchronization and load imbalance overhead we'll definitely talk about in the later parts of this course. And if you actually have a fourth one, I'd be really interested to learn. OK, so this is an example of sequential bottleneck, Amdahl's law. As you increase the parallel fraction from 0 to 1, this is what happens to speed up. And for different numbers of N. This is assuming, again, parallel partition is perfectly parallel. And if you look at this, the takeaway here is, and this is for N equals 1,000, N equals 10, N equals 100. If you look at this, you get high speed ups, high meaning higher than 10, only if your parallel fraction is very high, right? Greater than 92%. So you get most of the benefit of parallel processing if your parallel fraction is high. If you're going to have a parallel fraction that's small, don't bother designing a multi-core processor, for performance reasons at least. That's the key takeaway. And this is actually exactly the reason Cray was a supercomputer company, right? When they designed Cray 1 in 1970s, they had the fastest SIMD unit, vector processing unit in the world. But they also had this fastest scalar processing unit in the world also. If you look at Cray 1's design, it has a scalar processing unit design, and that has the highest frequency of its time. And the reason was exactly this. They had the sequential bottleneck in the parallel application, which their applications looked like this, basically. They were doing operations on big matrices, and these were the parallel tasks. This is the SIMD operations. You could think of them as parallel tasks in GPUs today. These are the SIMD operations that are almost perfectly parallel because you can divide your matrix into equal chunks, and you can do the same operation in that matrix. But then you had these serial portions of the program that aggregated the results. These are called reduction operations in vector processors. And this serial portion, even if it's 25% of your program, then the maximum speed up you can get an infinite number of processing elements is 4 times, right? And that's exactly the reason Cray had the fastest processing, scalar processing unit, which executed these tasks at the time, because of this picture and because of this picture also. Now, if you can minimize these, then you don't have a problem, if you can make it 0%, but that doesn't happen. Okay, so all parallel machines have the sequential bottleneck. This, even Google cannot escape this. They have a big parallel machine, warehouse scale computer, but they cannot escape this also. And non-parallelizable operations on data lead to that sequential bottleneck. And there are many reasons for this. This is one reason. This is another reason from one of the papers that I've assigned. Basically, this is, again, a dynamic tasking problem. And if you look at this, you have an initial part that prepares the threads and a print solution part that also prints the solution, which are not parallel. But you also have parts that are critical sections over here, which we will get to later on. So if you look at this, the execution of the program looks like this. This is a more realistic program, or at least a less amenable program to extremely high parallel processing. You have this part that's serial, you have this part that's serial, and this is the parallel part. But if you look at the parallel part, there's a lot of synchronization overhead because some processors need to access this task queue that we've discussed earlier. And task queue accesses are actually critical sections where if two processors need to access the critical section at the same time, one of them needs to wait. Okay, I think I'll cover this and then we can finish. So bottlenecks in parallel portions, synchronization operations. These are operations manipulating shared data. These cannot be parallelized. Locks, mutual exclusion, barrier synchronization are examples. And this leads to communication. Tasks may need values from each other. Now, this becomes interesting because now you need a scalable interconnection network if this communication actually happens. This causes thread serialization when shared data is contended. So this is a bottleneck in parallel portion. The second is load imbalance. Parallel tasks may have different lengths. And if you look at the previous picture, and we've discussed this, but this picture is not beautiful also, right? You have these parallel tasks, and some of them end here, some of them go down here, some of them end early, some of them, and they all end at different times if you cannot balance them really well. And as a result, you have that overhead. That could be because of imperfect parallelization, as we discussed, because the programmer did not know how to chop the tasks into equal pieces, equally executing equal time pieces. Or it could be because of microarchitectural effects, because some task may be accessing a bank that's contended, whereas another task may be accessing a bank that's, that only itself is accessing. And keep this in mind also. We'd like to figure out these effects and get rid of them. This reduces speed up in the parallel portion. And the third thing is resource contention. Parallel tasks can share hardware resources and they can delay each other. And this is actually true for software resources also, but we'll focus on hardware resources. The reason here is replicating all resources is expensive. You could replicate everything, but this is expensive. In fact, you would like to share sometimes so that you can communicate faster. But this leads to additional latency that's not present when tasks are run alone. And as a result, you get these bottlenecks in the parallel portion. Okay, maybe I should stop here because you have a deadline with the camera. And we'll pick it up after 5 minutes.